Okay, let's dive right into this explainer and completely demystify the hardware design life cycle. We're talking about taking a device from a tiny spark of an idea in your head all the way to a fully optimized physical circuit board. Whether you're aiming to build rock-solid power electronics, crazy advanced digital systems, or maybe just the next big smart home gadget, understanding this exact pipeline is absolutely vital. Today, we're going to break down the workflow that actually brings a circuit to life. We'll be pulling insights straight from KiCad's official documentation, Altium's high-speed design guidelines, and JLC-PCB's deep dives into industry-leading microcontrollers.
Here's what's on our agenda for today. First, the PCB design workflow. Second, drawing the blueprint. Third, taming high-speed signals. Fourth, choosing your microcontroller. And finally, power and connectivity.
Section 1. The PCB design workflow, from schematic to physical board.
Think about the fundamental difference between a symbolic blueprint and a complex physical layout. In the KiCad workflow, you always draw the schematic first. You're using basic shapes, right? Zigzags for resistors, maybe triangles for op-amps. This just shows exactly which components you're using and how they connect. But then, we have to move to the physical realization of that schematic. That's the board layout. This is where footprints, which are essentially just sets of copper pads that perfectly match the physical pins of your real-world components, are positioned, and actual copper tracks are routed to make the connections you laid out in your original design.
Now, to keep all of this organized, KiCad uses a strict project-based workflow. It keeps your schematics, your layouts, and your libraries tightly integrated. Think of a project as a unified folder. It contains your main project file, your schematic file, and your board layout file. And this is a huge deal because a lot of your project-related settings, like your design rules, are stored right there at the project level. If you try to open a board file outside of its associated project folder, you're probably going to lose critical design information. Everything has to stay together.
Section 2. Drawing the blueprint, creating the schematic in KiCad.
So how do we actually start? Well, the crucial first step is configuring your symbol library table so KiCad knows exactly where to find the parts you need. The very first time you boot up the schematic editor, you're going to get a prompt. This symbol library table literally tells KiCad which symbol libraries to use and where they physically live on your hard drive. The easiest and recommended path here is just to copy the default global symbol library table. That way you get instant access to KiCad's massive user-contributed repository of symbols right out of the gate.
Once you've got that configured, the fun begins. You can easily pull these visual representations directly onto your canvas. You might drop a Q101 transistor symbol right next to a U201 logic component. The whole design process at this stage is just adding these symbols, wiring their pins together, and then, crucially, assigning a physical, real-world footprint to every single one of them.
But listen, here is the most important takeaway for this section. You absolutely must follow this exact pipeline if you want your design to translate into a functional manufacturable board. First, draw the schematic. Second, pass an electrical rules check or ERC. Third, transfer it to the board editor for layout. Fourth, run a design rules check, the DRC. And fifth, generate your fabrication outputs. You literally have to hit every single step in that exact order, no skipping.
Section 3. Taming high-speed signals when traces become transmission lines. Now, you might be wondering, at what exact point do simple copper wires suddenly start behaving unpredictably? Altium's guidelines actually point out a really common misconception here. Say you have a 100 MHz clock signal. You'd probably assume 100 MHz is the highest frequency in your system, right? Wrong. The real issue stems from the rise and fall times of that near square wave signal. Sharp transitions from digital low to digital high contain way higher frequency content than the fundamental frequency itself. Get this, a 100 MHz signal with a 1 nanosecond rise time actually has a bandwidth of about 500 MHz.
And here is your aha moment. Once a trace exceeds what we call its critical length, it fundamentally stops being a simple wire and becomes a distributed length transmission line. Altium defines this critical length as the point when a trace exceeds 1/12 of the wavelength in the dielectric, which is just the non-conductive fiberglass material of the board. At this point, the basic rules of lumped elements go out the window. Now you have to start worrying about signal integrity, reflections from impedance mismatches, and electromagnetic interference. It's a whole different ballgame.
So how do we prevent the absolute nightmare of crosstalk and interference? Well, Altium gives us these rapid-fire layout rules to tame high-speed signals. First, keep your traces as short as possible. Simple enough. Second, always, and I mean always, have a ground or relevant power reference plane adjacent to your signal plane to maintain proper return paths. Third, and this is massive, never split a reference plane underneath your traces. For AC signals, the return path actually travels directly below the signal trace right in that reference plane. You also want to use thin dielectrics for tight coupling, and you absolutely must control your trace impedance, meaning you adjust the trace width to perfectly maintain a standard, like 50 ohms.
To further tame these signals, we rely heavily on the 3H rule. It's basically the golden standard for separating high-speed traces to keep your signal clean. To minimize crosstalk, you obviously want to keep different high-speed traces as far away from each other as possible, and especially far away from noisy components like inductors. So, the 3H rule dictates that traces should be separated by at least 3 times the height of the dielectric that sits between the signal layer and the next ground or reference layer. Stick to that, and you'll save yourself a lot of headaches.
Section 4. Choosing your microcontroller, the brain of the device.
All right, moving on to the ultimate showdown, the deterministic rock-solid precision of the STM32 versus the wireless flexibility of the wildly popular and much cheaper ESP32. JLCPCB's engineering analysis poses a fantastic question here. If the ESP32 is so cheap and already has Wi-Fi and Bluetooth baked right in, why in the world would anyone still choose the STM32? Well, it completely depends on what your product actually needs to do. Let's look at where each of these chips truly shines.
The STM32 easily justifies its higher price tag if your project demands flawless motor control, robust industrial communication, or medical-grade safety. Its Cortex-M processor handles interrupts in a strictly bounded, predictable number of clock cycles. We call this deterministic control, and it is absolutely mandatory for real-time adjustments like PID loops or multi-phase motor control. On top of that, the STM32 offers incredibly accurate linear analog-to-digital converters, native industrial protocols like CAN-FD, and safety-critical certifications. Plus, ST guarantees a 7 to 20-year longevity for these chips. They aren't going to just randomly pull the plug on your supply chain.
On the flip side, the ESP32 absolutely dominates the smart home space. Why? Because it handles all the complex RF routing and pre-certification for you. Every classic ESP32 ships with Wi-Fi and Bluetooth right on the board, and the newer ones, like the ESP32C6, even integrate Matter, Thread, and Zigbee. By utilizing their pre-certified modules, you are literally saving months of agonizing FCC compliance work, because all the physical RF routing, the matching networks, and the shielding are already done. It is undeniably the king of rapid network-bound consumer electronics.
Section 5. Power and connectivity, hard data on performance and sleep.
Now let's look at the raw data. The STM32 has a massive lead in raw single-thread processing power, which you absolutely need for heavy digital signal processing. Just look at the CoreMark scores. The STM32H7 clocks in at a massive score of 2010. By comparison, the ESP32S3 sits at 613. Sure, the ESP32's dual-core architecture helps with overall throughput, but maintaining those network connections eats up a huge chunk of its processing budget. If you're doing intense DSP, audio, FFTs, or running 1 kHz sensor fusion, the single-thread performance of the STM32 is just unmatched.
But wait, what about power consumption? This is where things get really interesting. The ESP32 draws significantly more current, especially during active RF transmission. The STM32 completely separates itself here, literally by an order of magnitude. Get this, an STM32U5 in shutdown mode draws a microscopic 0.3 microamps, while an ESP32 can get down to a respectable 5 or 10 microamps in deep sleep. Its active current spikes heavily. We're talking jumping all the way up to 240 milliamps during Wi-Fi transmission.
To put that into real-world perspective, an STM32 can run for years on a tiny coin cell battery. An ESP32, it's much better suited for something plugged into the wall or running off a large LiPo battery. In a practical application, say an environmental sensor waking up every 10 minutes, an STM32-based LoRa sensor will easily last 3 years on a standard CR2032 battery. If you put that exact same workload on an ESP32, it's completely dead in about 3 months. So as you sit down to draw your next schematic and route those tricky high-speed lines, which brain are you going to choose? Will you demand the rigorous, ultra-low-power precision of the STM32? Or will you leverage the incredibly cheap, wireless freedom of the ESP32? Ultimately, the hardware you select dictates the entire future of your product. So what kind of future are you building? Until next time, keep learning, keep designing, and keep building.